Okay, so in the last class we started off with module 4, which is colloidal interactions in terms of looking at what are called as electrostatic interactions, or also called as electrical double layer interactions. Okay, so we had briefly talked about what is the importance, why are we trying to look at this particular module, and also about what are the different ways by which the particle surface gets charges. Okay. I had also mentioned what is a electrical double layer concept as well. I just want to quickly recap that. So, what you are looking at is a colloidal particle which has negative charges, which is represented by minus here, and the moment you have and of course, you are going to have these are the counter ions, right. These are the counter ions in solution, and whenever you have a charged species, it is going to generate, this charged species is going to generate electric field, right. And because of the electric field that is generated because of the charges on the particle surface, it is going to attract oppositely charged ions, okay, or the counter ions are going to be attracted to the surface because of the electric field. Okay. Therefore, you are going to have a layer of charges on the particle surface, okay, and of course, you are also going to have the charges in solution, which are kind of attracted to the surface because of the electric field generated because of the charge on the surface, and this particular arrangement, okay, where you have two layers of ions, okay, which are opposite in polarity. That is what is called as a electrical double layer. Okay. What is really important when we are trying to look at electrical double layer interactions is that we are interested to ask questions such as what is the spatial distribution of co-ions and counter ions in solution. Okay. This is the question that we are trying to ask, and it turns out that answering this question is really important if you want to understand the electrostatic interactions or the electrical double layer interactions. So, therefore, we are going to look at some models in which people have proposed different models which kind of depict what is the distribution of counter ions and co-ions in solution. Okay. So, in that context there are some old models which are not valid anymore. I mean, but this kind of this capacitor model which I am going to discuss, this started off the field of electrical double layer models, okay. And then the more recent ones talk about what are called as a Debye-Huckel model for electrical double layers, or Gouy-Chapman model for electrical double layers. So, these are more of recent developments. So, we will try and look up each of them and then discuss a little bit about what these models say. Okay. In that context, the first model that we looked at was something called the Helmholtz model for electrical double layer, okay, in which it is assumed that the counter ions, okay, these are the ions which have the charges that are opposite in polarity to the charges on the particle surface. In this case, the particle surface is negatively charged, and these are the counter ions which are positively charged. The counter ions directly bind to the surface. Okay, they are kind of attached, to the charged surface, and they kind of try and neutralize the surface charges. Okay, very much like a capacitor, right. When I say neutralize, you can see that, right, for every there is an ion pair, right. For every charge on the solid surface, there is a charge in the solution which is kind of attracted to the surface, and they are tightly bound, and the charges in the solution, they essentially neutralize the charges on the particle surface. Okay. That is one of the simplest model of electrical double layer. Okay. And so, to understand, so what we are trying to do is we are trying to develop an expression, okay, for a kind of a quantity which is, if I have two, so this basically arrangement tells you something like capacitor, right. So, I have some charge, some plate which is negatively charged, I have another plate which is positively charged. Okay. So, we would like to relate what is the potential drop. Okay. If I say that the potential drop is delta psi, okay, del psi, and if the distance between the two plates, if they are at a distance x1 and x2, okay, your delta is going to be x1 minus x2 or x2 minus x1, that is the separation, okay, of these plates. We want to relate delta psi by delta to parameters such as the surface charge density, okay, and the dielectric constant of the medium between the two plates. Okay, that is what we would like to go about. Okay. So, in doing that, we would like to exploit a concept called is a concept of line of force. Okay. You would have seen in electrostatics pictures like this. Okay. If I have a plus q charge or a minus q charge, you would have seen some lines like this. I do not know if you remember. What are they? They are the electric field lines, right. Okay. By convention, if it is a negative charge, then the field lines are going to be inward, and if it is a positive charge, the field lines are going to be outward, right. So, this electric field, right, it is actually you can calculate it as this electric field that is generated because of a point charge. It essentially is given by force divided by the charge, okay, and the force is 1 over 4 pi epsilon naught into epsilon r into r square into q, right, that is F by q. Now, what I can do is I can express this as q divided by epsilon naught epsilon r, and I have 1 over 4 pi r square. Okay. Now, instead of assuming a point charge, if I assume that the charges are located on the surface of a sphere, this 1 over 4 pi r square gives me the area. Therefore, I can write this as q divided by a into 1 over epsilon naught epsilon r. Okay. Therefore, this q divided by a is essentially the surface charge density, that is the number of charges divided by area, that is going to be sigma star divided by epsilon naught epsilon r. Okay. And we know that, so whenever we talk about this, the understanding is, if I have a test negative charge, and if I bring in a test positive charge, and if I bring in a test negative or a positive charge near it, it is going to, each of the charges are going to experience some force, right, and you can imagine that this force acts along some line, okay, and this is an imaginary line, and that is what is called as a line of force. Okay. Depending upon the number of charges that you have, there are going to be so many number of lines of charges. Okay. In a way, so you can think about line of force as a imaginary line over which a test charge, okay, which is going to be brought into the vicinity of a either positive or a negative charge, the force that the test charge is going to experience. Okay. So, depending upon the polarity of the charge, this force can be either attractive or repulsive, right. So, we are going to use concept like this. So, now, yeah, it is same as field line. So, see, I mean, so see, when I wrote this field line, right. So, I mentioned that, so I can also imagine, instead of calling this as a lines that come out because of the field, I can also say that you can imagine that there are, if I have two charges, there is going to be some force of attraction or repulsion, right. Now, and the force of attraction or repulsion is going to act along some line. Okay. If I take a point charge, it is going to be acting along some line, right, and this line is what we are talking about.
Okay. So, lines of force is for some charge and field line is for a unit charge.
Yeah, I mean, so if you see, when you talk about expressing, the only difference would be that if you talk about forces, I would have to worry about resolving them if they are not acting on a particular line and stuff like that. Okay. So, you can okay. So, now what you are looking at is two arrangements. Okay. One is so you can imagine the minus, right, to be the charges on the solid surface, that is the charges on the solid surface, and these are the counter ions. Okay. That is a capacitor like arrangement, and in this case they are in vacuum. In this case there is a medium of some dielectric constant epsilon between the two plates. Okay. So, we are going to all these lines that you are seeing, these are the lines of forces, right, and depending upon the charge on the each plate, the lines of forces are going to be different, right. That means, the spacing between these lines depends on the total charge, right. If I have a very high Q, you are going to have many more lines closely spaced, and however, if if the Q is not very high, you are going to have sparsely populated lines, right. Now, so what is and by convention, as we said that the lines of force, they start from positive and they go towards negative, right. That is the convention that is followed. Okay. Now, if the plate carries a charge Q, okay, and if the area of the plate is A, then I can define the surface charge density, which is Q divided by A, right. Now, the lines of forces that you see, they start from one charge surface and they terminate at the opposite, the place which has the opposite charge, right. Now, we kind of derived this a while ago. So, this electric field that is generated, okay, in the case where you have vacuum, I can write that as the surface charge density multiplied by 1 over epsilon, right, and because Q by A is defined as sigma star, therefore, E naught essentially becomes sigma star divided by epsilon. And similarly, if I replace the vacuum with a medium with a permittivity epsilon, I am going to write E epsilon as sigma star divided by epsilon naught epsilon r, right. And the understanding is that the number of lines of forces is a measure of the field strength. Okay. So, the more the number of lines of forces, more is a field, and of course, it is dictated by whether the region between the two plates has vacuum or some medium with a dielectric constant epsilon r. Okay. Okay. So, now this electric field and the potential, okay, they are related this way. Electric field is a negative gradient of the potential. We are going to use potential in the calculation that involve electrical double layer, because of the fact that we know that the force depends on the charge. If I know the force, I can get electric field. If I know electric field, I can get psi. Okay. Therefore, if I have a way of finding out what is the surface potential, okay, then I will have a way of telling something about what is the charge Q on the particle surface. Okay. So, but the reason why everything that we are going to do will have psi, because doing math is much easier if you work with psi. Okay. So, now so this del psi by del x, if I assume a small drop in the potential, I can replace this d psi by delta psi and dx by delta, okay, and that is equal to sigma star divided by epsilon naught epsilon r, okay, where delta psi is the potential drop between the two plates which are separated by a distance delta, and this particular expression, it actually relates the charge density, which is sigma star, okay, and the potential difference, that is delta psi, okay, and the distance of separation between the two plates, which is delta. Okay. Now, so so in the electrical double this essentially is the electric Helmholtz model for electrical double layer. What you are seeing is a depiction where this alpha and beta, they essentially refers to two phases. In this case, so we have we had a charged surface, right, okay, and they are going to be counter ions. Now, when I say two phases, in this case, one is a solid phase, other one is a liquid phase, right. Now, and this kind of arrangement that we are seeing, it is actually seen at the interface, right, at the interface of the, as I go from one phase to the other phase, at the interface is what you are going to have arrangement like this, right. So, this is alpha psi beta and psi alpha refer to the potential at the two phases alpha and beta, and they are separated by a distance x1 and x2, and what this particular model predicts is that the variation of potential in the gap between the two plates, the variation is linear. Okay. So, the variation of the electric potential across the double layer according to the capacitor model, there is a linear variation of the charge. Okay. So, if I know what is the potential here, if I know what is the potential drop, okay, that is delta psi is equal to, say, if I say 0.1 millivolt or something like that, I should be able to calculate what is how the potential varies across the entire gap. Okay. So, that is the what is called as a electrical double layer model, the capacitor model for the electrical double layer. So, we had again done this. So, if you take a case where I have a charged monolayer, okay, charged monolayers are found in several, you can imagine that I have a spherical particle, okay, and say that I have charges on the surface, okay. So, and if I look locally, I really have a flat region, because if I compare the size of the ions corresponding to the size of the particle, you can imagine it is a flat line, right. So, therefore, I am really going to have a charged monolayer in this case. Okay. Other way to imagine charged monolayer could be, I have a container, I have water in it, I add charged surfactant, okay, and charged surfactant are represented by something like that, right. It could be positively charged or negatively charged. Now, because these surfactants have the tendency of going to the interface, if I look at interface, the arrangement looks something like this, okay. Interface will have, okay, and because each of them will be charged, and if there is dissociation, I am going to have a monolayer of surfactant that is charged. Okay. So, if you take a case of a charged monolayer where the monolayer has one charge, okay, it has one charge per 10 nanometer square area. Okay. So, I am basically looking at an arrangement either like this or arrangement like this. I take an area which correspond to 10 nanometer square. Okay. If there is only one charge on the surface, then I can calculate sigma star, the surface charge density, that is one ion per 10 nanometer square. It becomes 1.6 10 power minus 9 coulombs per ion, right. That is the charge on the one ion, okay, divided by 10 nanometer square. If I do that, I get sigma star to be 1.6 into 10 power minus 2 coulomb per meter square. Okay. So, now to calculate, now if I assume that this is immersed, this is in water, okay, I have a charged monolayer, and if that is in water, then I can calculate what is epsilon s, right. We can go back to this expression. So, epsilon s is essentially sigma star divided by epsilon naught epsilon r. I know what is sigma star divided by, this is epsilon r, this is epsilon naught. So, I get epsilon a, E epsilon as 2.63 into 10 power 7 volt per meter inverse. And typically, if when we talk about the potential drop across such charged monolayers, okay. So, if I look at the potential drop in case like this, okay. So, it typical value that people talk about is about 0.1 volts. If I substitute for 0.1 volts, I can actually get delta. Okay. So, this delta, it is in a way, it tells you something about the thickness of the electrical double layer. Okay. The double layer in this case corresponds to this and this, right. The thickness of the double layer is given by delta, and it turns out that I can calculate that, and it turns out to be something like 4.4 nanometer. Okay. So, therefore, you can say that the electric field that is generated by the surface charges, it is in molecular dimension, right, because of the fact that the numbers are 4.4 nanometer, it is very close to the molecular dimensions, right. So, that is the kind of conclusion that you can draw if you work with what is called as capacitor model or the Helmholtz model for electrical double layer. Okay. Okay, and if you look at several different problems, and if you calculate the double layer thickness, it will be few nanometers in dimensions.